In the previous lesson, we saw how to estimate toggle rates and activity factors in each of the logic gates within a Verilog or VHDL RTL design, and that would, together with the capacitance at each output, the toggle rate, the power supply voltage, will allow us to estimate the dynamic power. But the switching power, the dynamic power that is due to the actual computation is not enough to estimate the total consumption of digital VLSI IC. In fact, the equation with the total capacitance only refers to the switching activity that is associated with charging the output capacitance. There is switching activity, there is power that is consumed internally within each gate, that is lost internally within each gate. This is the leakage power, the leakage power and the crowbar current that will not be able to be estimated from that analysis alone. So in this study, in this lesson, we will talk about how to estimate these leakage power, as well as the short circuit crowbar current power, which is associated with switching and dynamic activity. Okay, the steps for converting an RTL, Verilog or VHDL design into a final circuit level representation netlist that can be estimated is as follows. The RTL design, the high level RTL design, is synthesized to break it down into elementary logic gates, and then there's some optimization of logic function and placement reordering of flip-flops that could occur in more advanced synthesis software. This is performed by the synthesis software. After the low-level definition of the design is obtained, each of the low-level gates, for instance, the NAND gates, NOR gates, AND gates, OR gates, are then mapped to specific gate level designs, that is transistor level designs of gates that can be manufactured by a fab. And the description of this set of very specific transistor level gate designs, logic gate designs, is contained within a library file, and they're collectively referred to as the standard cell library. And the standard cell library is a library of all possible logic gate implementations up to the transistor level that can be fabricated by a particular fab house. And the standard cell library is associated both with a fab house and with a particular process. Let's say if you're talking about a 45 nanometer process, it means the standard cell library for a 45 nanometer process is the library of all logic gates, digital logic gates that are available that can be fabricated in that particular 45 nanometer process library. If there are two 45 nanometer process libraries in the fab, then you would have two standard cell libraries. If there is a 90 nanometer process, then you will also have a standard cell library for a 19 nanometer process. So in the synthesis stage, and typically for a specific design, a standard cell library associated with a fab process has to be selected. And out of the many the many files that are provided with that standard cell library, a particular group of files or a single file called a Liberty file with the extension .lib contains the timing and energy definitions of each and every gate. So when we talk about a detailed model of transistor level model of gate, these standard cell library files will have different timing and energy parameters for gates of different configuration. Let's say 2 input AND gate, 3 input AND gate, 2 input NAND gate, 4 input NAND gate, and for gates with different sizes as well as gates with different speeds of operation. So in short, the .liberty file, which is one of the files in the standard cell library, contains the timing definitions as well as the short circuit power definitions. This is the switching energy per transition, and the leakage power definitions for each and every possible logic gate that can be fabricated in that process. Besides the values for the switching energy, the leakage, and the timing is associated with specific PVT situations. So the .lib file will have to define each of these values under, let's say, a nominal process, a nominal voltage, or nominal temperature, or it could be a fast NMOS, fast PMOS process at a plus 10% voltage, a supply voltage, at the maximum junction temperature. There could be various combinations of PVT where the energy per transition, the switching energy per transition, the leakage power could be defined in the Liberty file. So let's take a quick look at the format of a .lib file. The .lib file, as illustrated here, contains several portions, and what I've extracted is the header part. And as you can see from the header part, we are actually using typical delay, power, capacitance model. The name of this library, which is the name of this process, is GSCL 45 nanometer. So this is a 45 nanometer process from a particular fab. You can inspect this file, which has been provided to you. And basically the file, the header would start by defining the time units, the units, the time of time, voltage, current, resistance, leakage power, and capacitance. So here, any capacitance value that is specified will be specified in units of 1 picofarad. Any voltages will be specified in units of volts, and any currents will be specified in units of microamps. And in this particular file, only parameters of energy, leakage power, switching energy, leakage power, and switching delays are defined at a nominal voltage, nominal process, a nominal voltage of 1.1 volts, and a nominal temperature of 27 degrees Celsius. And so the operating condition of all the energy, leakage, and time delay specifications in this library file are given for nominal conditions. Now, for energy estimation purposes, it is if you would be advised to simulate and estimate the energy at nominal situation, because that is what you would expect in the best and most well-controlled environment. But we would also like to understand the worst case energy consumption. And the worst case energy consumption happens at the PVT corner, where there is fast NMOS, fast PMOS, 10% higher voltage, supply voltage, and at maximum junction temperature of all the logic gates. So it is recommended to actually simulate the energy consumption at the nominal PVT as well as the FF plus 10% and maximum junction temperature PVT condition. Let us proceed to study the format of the .lib file in the next parts. Here I'd like to draw your attention to the definition for one out of the many logic gates that can be implemented. In this case, we are considering a 2-input, 1-output NAND gate. And this NAND gate has an area of 1.877200, and the leakage power consumed by this NAND gate is 3.29145 nanowatts. Pay attention that we know that the leakage power is in nanowatts because of the unit definition here. There is the input pins are labeled pin A and pin B, and the capacitance, the average capacitance at the input A is given by these values, whereas the specific capacitance associated with seen by a rise transition is given by this value, and the specific capacitance seen by a fall transition is given this value. These capacitance values can be used to compute the total charging voltage, that is the voltage of the output parasitic capacitance of a gate, the wire capacitance, as well as the capacitance of all the loads connected to it. So for instance, if you're estimating the power consumption at a particular logic gate, which drives the input of this NAND 2 by 1 logic gate, you would read off the capacitance values at these points. And if you wanted a more cycle accurate simulation, you would actually select the capacitance based on the actual transition activity that you can obtain from the .vcd file. Now, so far we have discussed how you would obtain the the characterized values of leakage power in a gate, as well as the power of charging the output capacitance. But we've not talked about how you would estimate the short circuit power, which is still a dynamic power, but it is not directly related to useful computations. And we can proceed to study that by first saying that the short circuit dynamic power consumption is typically specified in the form of tables. And here we see the definition of that table. The table is given by two index, where variable 1 is the index of rows, and variable 2 gives us the index of columns. So in the rows, and specific values of short circuit energy consumed will be specified as a function of total output net capacitance, and this output net capacitance is only the diffusion parasitic capacitance seen at the output gate, and will also depend on the input transition time, that is the speed at which a rise transition or fall transition happens in your particular design. And the specific values of these will be specified in the index. So let's look at an example of how this is specified. Here is the second part of the NAND 2 by 1 gate that we have been studying. And this is now a section of code under the output pin Y. So scroll to the section where it says internal power. And this section here with related pin A is the energy consumption, the energy consumed by switching activity, that is the short circuit current consumed by switching activity associated with a rise transition on the input pin A, and a fall transition on input pin A. And this section of the definitions only refer to rise transitions on input A that cause a transition at the output pin Y, or fall transitions at the input A which cause an output transition in output pin Y. For rise transitions or fall transitions at inputs that do not lead to an output transition, we will cover how a .liberty file can specify the power consumption there. But in this particular GSCL 45 nanometer .lib process, those parameters are not specified. Therefore, we only associate the charging capacitance of the input pins with input transitions that do not cause output transitions. So let's jump straight into the meaning of this file. As we can see, the table of energy transitions is using the energy template 6 by 6. And just to refresh our memory, here, just hold on here. Variable 1 is the total output capacitance in picofarad, and variable 2, which is the column, is the input transition time in nanoseconds. So this table specifies the rise power for total output capacitance of gates with 0.1 picofarad, 0.5 picofarad, 1.2 picofarad, 3, 4, and 5 picofarad output capacitance, and this is an indirect specification of gate size. And it also specifies the energy that is consumed with a 0.06 nanosecond rise transition, 0.24 nanosecond rise transition, 0.48, 0.9, 1.2, and 1.8 nanosecond rise transition. And these power values here, so for instance, let's take this power value. This is at row 3, corresponding to 1.2 picofarad output capacitance, and column 2 corresponding to 0.24 nanosecond transition time. So 0.004552 nanowatts is consumed on every rise transition at input pin A that leads to a output pin transition for a NAND 2 gate that has 1.2 picofarads output capacitance, and the rise transition at the input is 0.24 nanoseconds. So this is how we are able to read the values from the dot liberty file. So a similar set of specifications is also seen for pin B. Okay, you can have a look at pin B there. Right. And now we will proceed to ask the question, how does the dot liberty file also permit us to specify dynamic switching power associated with the short circuit current for input transitions that do not lead to output transitions? Again, the dot liberty file provides this format, and the only difference is that you specify a when condition, and here the condition states that and this is specified under the definition of the input pin A1, and this internal power is consumed when a second input pin A2 is set at 0 and the output pin Zn is set at 1. So when the second input pin is set at 0, A2 is set at 0 and Zn is 1, a rise transition on input pin A1 does not lead to any transition at the output, but it does consume energy, which is given by these values under specific rise transition times given by this index. So a similar state dependent power consumption is also seen in flip-flops. Again, this will be defined under the input pin section, not the output pin section. And this does not only apply to switching or dynamic power, that is power that's associated with switching activity. State-dependent leakage power can also be specified. Instead of the standard cell leakage power here, you would define a leakage power syntax here by specifying when, that is, and this is the leakage power 1.17 nanowatts for an inverter when the inverter input is at logic 0, and when the inverted input is at logic 1, the leakage power consumed is 0.23 nanowatts. The general leakage power here is simply the average leakage power of all states in the gate. So you will find that this leakage power 0.7 is actually the average of this as well as this. So your models, depending on the degree of accuracy detail that your fab house provides you, your model may or may not have state-dependent parameters, but it will at least have the average leakage power, the average dynamic power associated with short-circuit currents for output transitions associated with input transitions.